Okay, so microphone is open. Welcome back to our video, and in this video we will be covering physics. Basically, there is a target to finish the physics AS part for you guys in very short time. So I'm not sure what lessons exactly will we be covering in this video, but we will be covering big part inshallah. So starting with unit 1 in here, basically we have that it has nuclear physics, particle physics, quantum physics, current and resistance, DC circuits, internal resistance, and alternating currents with some of energy particles, photoelectric, quantum, electricity, etc. So this video is for international AQA level, right? But it's gonna might be also useful for OCR, normal AQA, Excel, and somehow CAIE. So we will be studying from those notes, or at least tell you what is it from those notes. We have movements and their errors, particles and radiation, waves, mechanics and material, electricity, further mechanics, thermal physics, fields and their consequences, and the nuclear physics for A level paper 1 and A level paper 2, of course. And then paper 3, practical cells, etc. with one off. So I'm just telling you it's the same thing. Let's get started and get in deep into it. So and here in unit 1 we have particles, quantum phenomena, and electricity. What do we know about particle physics and what do we want to know? We know that inside the atom we have electrons, we have protons, and we have neutrons. We already know that a protein has relative mass of 1, neutron has relative mass of 1, electron has negligible relative mass, and has relative charge of positive 1, the proton, neutron of 0, electron of negative 1. But what we don't know is that they have also something called absolute mass and absolute charge that we're going to be talking about right now. Before we go into these, did you know that electron, which is negatively charged in cells and subshells, are around the cell nucleus, and that the nucleus composed of protons, which are positively charged, and neutrons, which have no charge? The nucleons are basically the protons, and the neutrons, which is basically make up the mass number. And then we have something important, something more into electricity, etc. The coulomb. The coulomb is unit of charge equal to the electrical charge transferred by a steady current of 1 ampere in 1 second. It can be calculated as Q equals IT, ampere or current times time. So of 1 ampere in 1 second. And then we have the elementary charge. The elementary charge, basically the electric charge carried by a proton, or equivalently the absolute value of the electric charge carried by a electron, as electron is negatively charged. Here it is, right? So the absolute charge for the proton must be positive, for the electron must be negative. They are the same thing. For proton, it's positive 1.60 times 10 to the power of negative 19. For electron, it's negative 1.60 times 10 to the power of negative 19, or you can find it in some notes 1.67. For the neutrons, has no absolute charge. And last thing we'll be covering in this part is the absolute mass, also 1.67 over here. The proton has a relative mass of 1.67 times 10 to the power of negative 27. Neutron has 1.6 times 10 to the power of negative 27. But the electron has much less, has 9.11 times 10 to the power of negative 31. If you say how much less, with this is 9 and this is 1, see the power, negative 31 and negative 27. Negative 31 means it's way more less. It's going to go 31 times, while this will go only 27 times. Okay? And a quick information that we need to know before we go to the next part is that the mass number is basically the nucleon number, which is made of protons and neutrons, while the atomic number is the number of protons. But did you know that when the mass number changes, there is a different type of atom occurs? Basically, it's called an isotope. But what caused mass number to change? Is it the proton number? No, never the proton number. It's always the neutron number. The isotope is an atom with the same number of protons, atomic number, but different number of neutrons, which is the mass number. And each different type of nucleus is called a nuclide. This is just a part that we need to know the normal base about. But now we will talk more about the charge and the fundamental forces. The specific charge. Specific charge is the charge of a specific particle divided by its mass. The nucleus of a hydrogen, which has one mass number and one atomic number, has charge of 1.60 times 10 to the power of 19 coulomb and mass of 1.67 times 10 to the power of negative 27 kilogram. Hence, its specific charge is 9.58 times 10 to the power of 7 coulomb kilogram negative 1. How did we find that? Because the specific charge is equal to the charge of the specific particle over its mass. Okay, so this is the first rule. But what about, we're just gonna finish this part. What is the fundamental forces for now? Basically, current theory suggests that there are only 4 types of interaction in the universe between the particles: gravity, electrostatic magnetic force, and the weak interaction. The gravity, this force acts between all particles in the universe and has an infinite range, however, reduces in strength according to the universe square law. At an atomic scale, it has negligible influence as it's the weakest fundamental force in the universe. Gravitation is mediated by the graviton, undiscovered. What about the electromagnetic force? This force acts on any charged particles. It can either be repulsive, which has same charge, or attractive, different charge. The electromagnetic force is responsible for keeping molecules together. The electromagnetic force is mediated by virtual photons. What about the weak interaction? This force acts on all known formations, or rather than all particles with half integer spin, quarks, leptons, and baryons, but not bosons, elemental bosons, and baryons. The weak interaction acts over a very short range, roughly an attometer 1 times 10 to the power of negative 18. Over this range, it's many times stronger than gravitation, roughly 10 to the power of 33. The weak interaction is responsible for electromagnetic decay. The weak interaction is mediated by W and D bosons, which are the elemental particles. And last type is the strong interaction. So we have weak interaction, strong interaction, gravity, electromagnetic force. Strong interaction. This force is observable in 2 areas. On the smaller scale, the stronger interaction is responsible for holding quarks together in hadrons. On the larger scale, it binds protons and neutrons together inside the atomic nucleus. Nucleolus. When talked about in terms of binding protons and neutrons together, it's referred to as the strong nuclear force or the residual strong force. The strong force binding quarks together is mediated by gluons, while the mediator responsible for binding protons and neutrons together is the pion or pi meson. What about the strong nuclear force? Here we did the fundamental forces, but what is the strong nuclear force or the residual strong force? Basically, the strong nuclear force overcomes the electrostatic repulsion between and keeps the nucleus stable and attractive between 4 to 0.4 fm. Fm is the femtometer, which is basically 1 times 10 to the power of negative 15 meter, and repulsive below 0.5 femtometer. Otherwise, the nucleus would collapse and be point-like. Keep all nucleons together, not just protons. Mediator of the nuclear forces are pions or pi mesons, by to the power of 0. Also called the residual strong force, as the strong nuclear is related to the strong force. The strong nuclear force is responsible for keeping nucleons together, while the strong force is responsible for keeping quarks together, mediator gluons. Okay, so we now go to the radioactive decay. We have the alpha decay, beta positive decay, beta negative, gamma radiation. And then we go to the electromagnetic waves. Okay. Starting with the first type of the radioactive decay, the alpha decay. It releases alpha particles, which are positively charged helium ions, and reduces the mass number of nucleons by 4 and atomic number by 2, as you see over here. The beta decay have 2 types of beta radiation, beta positive and beta negative. The beta positive decay has a name of positron, and the proton decays into a neutron, emitting an electron neutrino and a positron. The beta negative decay, the neutrons decays into a proton, emitting an electron and an electron antineutrino. Note that the bar above electron neutrino indicate that it is that antiparticle counterpart. The electron does not follow this rule, and instead, the positron is shown by change of charge, gamma radiation. When the alpha or beta decay occurs, the nucleus is usually left in an excited state and it subsequently releases a high energy photon, the gamma particle, to reduce this energy. Photon has no mass, gamma has no mass and no charge. Okay, um, I want you to know that the particle physics, or what we called earlier the nuclear physics, isn't done so far. There's still a lot of stuff, but it will be into things. For example, over here, the photons. Photons is under electromagnetic waves. We need to know that the speed of the wave is given by C equals F. I don't remember its name. Wavelength. Frequency by C over this equals F. Photons are emitted when fast-moving electrons stop. Electron jumps from higher quantum level, which is basically shell, and an atom, to a lower one, and the energy of an electron can be given by E equals hf, where h is constant, and it's called the Planck's constant and has value of 6.63 times 10 to the power of negative 34. As C is equal to F wavelength, this can also be shown as follows E is equal hc over the simple, and a laser beam consists of photons of the same frequency, hence can be shown as E equals nhf. Okay, what about the particles and the antiparticles? Basically, when a particle and its corresponding antiparticle meet, they annihilate and are converted completely into energy, found by E equals mc squared. It's also possible for a photon of high enough energy to spontaneously change to a particle and its antiparticle counterpart. This is known as pair production. Energy of a particle is usually measured in MeV, millions of electron volts, and is defined as energy required to accelerate an electron through the potential difference of 1 volt. 1 MeV is equal to 1.60 times 10 to the power of negative 13 joule. What about the antiparticles? Antiparticles, same rest mass as corresponding particle, same rest energy as corresponding particle, and opposite charge if the corresponding particle has charge. Note that the antiparticles are usually denoted with a line above, like for example, as shown. This, for example, V line above E is an electron of antineutrinos, with the exception of the positron, anti-electron, which is denoted by E positive. Rest energy, energy when stationary of a particle, can be found by E equals mc squared, where m is the mass of the particle when stationary and c is the speed of light. Pair production. It occurs when a photon with high enough energy changes into particle and its corresponding antiparticle. As one photon turns into two particles using E equal mc squared, the photon must have at least the rest energy of the two particles that it turns into. Hence, E0 is equal to mc squared. As two particles are produced, 2E is 0 is equal to 2 mc squared. Therefore, the energy of the photon must be E gamma is equal to 2E0, and as E is equal hf is equal to 2E0. Now we go to the annihilation before we go to the particle interaction. Annihilation. It occurs when particle and its corresponding antiparticle meet and convert themselves to energy in form of two photons as seen in the diagram. As two photons are produced using the equation above, it can be shown 2E gamma is equal to 2E0, hence E is equal to mc squared, hf is equal to E0. Particle interaction is the one we will be doing right now. We have the electromagnetic force, which occurs only between charged particles that have opposite charges as they attract and same charges repel. The mediator of the force are virtual photons, and they're called so as we cannot directly detect them, as if we did, we would stop the force from occurring. For the weak nuclear force, it's responsible for beta decay, which are both types, the beta positive and beta negative, positron and the beta negative. And also the weak interaction only occurs with leptons and hadrons. This explains why neutrinos are so reluctant to react with anything. The mediators of this force are bosons, which are three types, W positive, W negative, and Z. W bosons are each other respective antiparticle, which are the opposite charge, while the Z boson is its own and subsequently has no charge. Z bosons are not covered in this specification. So we need to know only about the W bosons. The non-zero rest mass and the short range bosons are relatively massive and consequently are high in energy, which means they have short lifetime, which leads to them only being able to act over small distances, typically 10 to the power of negative 17 meter. This is the end of this video. Have a nice day.